Okay, today we're going to look at the inverse of square matrices. So we're going to identify what they are, how to find the inverses using first Gauss-Jordan, and that'll work for any type of inverses. And then we'll learn the formula if we have a 2x2 inverse, and then how to solve systems equation using our knowledge of inverses, or application of it. So what is an inverse? Well, if you take a matrix times its inverse, and you get what's called the identity matrix, or if you take the inverse times the matrix and it also gives you the identity matrix, then you have, that's the definition of the inverse. The identity matrix is a special matrix in which it has ones at the diagonal and zeros in other entries. So this is a 2x2 identity matrix. And here is a 3x3 identity matrix. Now the key is identity matrix are always square, but notice you have you have ones along the diagonal, your leading ones. And then every other place is zeros. Everywhere else is zeros. That's called the identity matrix. So that a to the negative 1 is our notation for the inverse of a. And it's simply read a inverse, or the inverse of a. Okay, how to show if two matrices are inverses of each other? Well, you do what the definition just did. So to show that B is the inverse of A, I'm going to multiply B and A together and see if I get an identity matrix. And then if it works one way, it might not work the other way. So then I also have to multiply A times B and see if I get the identity matrix. So we'll start by multiplying B times A. Now remember, when you multiply two matrices together, you go over and down and sum those totals together. So that's going to be 1 times negative 1 plus negative 2 times negative 1, which is negative 1 plus 2. And now I want to move over and down for my first row, second column. Sorry, that gives me 2 times plus a negative 2. Now I'm going to do second row, first column, entry. 1 times the negative 1 gives me a negative 1 plus negative 1 times negative 1 is positive 1. Okay, now second row, second column, entry. Remember, over and down with a multiplication. 1 times 2 is 2. Plus a negative 1 times 1, which is negative 1. Okay, so let's see. That gives us 1, 0, 0, 1. So yes, we have the identity matrix. But now I have to prove it by taking B times A, because remember, order matters when multiplying matrices. Okay, our first row, first column entry, it'll be negative 1 plus 2. And then for my first row, second column entry, I will get 2 plus a negative 1, negative 2. Now moving down to my second column, second row, first column, I get negative 1 plus 1. Now second row, second column entry gives me 2 plus a negative 1. Simplifying those down, you get 1, 0, 0, 1. So that is also the identity matrix. So I have proven that matrix B is the inverse of matrix A, or matrix A is the inverse of matrix B. And notice the notation. So I say since A times B equals the 2x2 identity matrix, that's I sub 2. And B times A equals the 2x2 identity matrix, we know A is the inverse of B. All right, so special lines. If matrix A has an inverse, then A is called invertible. If matrix A does not have an inverse, it is called singular. A non-square matrix cannot have an inverse. So only matrices that have the same number of rows, same number of columns have inverses. Okay, a square matrix may or may not have inverses. So to have an inverse, it must be square, but not all square matrices have inverses. All right, what if, how do we find a square matrix? How do we find the inverse of any square matrix? Well, first you're going to write a 2 by 2n matrix. So we're going to double the number of columns that it has by writing the matrix A, the original matrix, dot, 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 the identity matrix for that square matrix. Okay. And then our goal is to, on the left-hand side, where you have matrix A, the original matrix, you're going to make that into the identity matrix using our elementary row operations that we learned. Okay. And then our result would be identity matrix, dot, 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 our inverse matrix. Now, A is singular or not invertible. We will get something that is impossible to do. And then we could always check our work if we want to. by multiplying our original matrix by our answer and see if we get the identity matrix, or vice versa, multiplying our answer by our original function and see if we get the identity. So let me show you how this is set up. So here is my original matrix A. Now I'm going to do dot dot dots. And now, since this was a 3 by 3 matrix, I'm going to do the 3 by 3 identity matrix over here. This is step 1, setting it up. Now, I'm going to do Gauss-Jordan elimination on the left-hand side until I get our leading ones and our rows of zeros. So we're going to rewrite that as matrix A, and we're going to rewrite it to make it look like the inverse matrix. So I was just going to be working with this highlighted side. Now, I already have a leading one in my first row, so I need to get zeros below it. So if I take the opposite of row 1 and add row 2, that'll give me a 0 in that first entry of row 2. I also need a 0 in row 3. So if I take -6 times my row 1, add it to my row 3, that'll give me a first entry of 0 in my row 3. So let's do that. Now my first column is complete. I have my leading one and my zeros below. So next step is to get the leading row and my second entry, second column, which I already have. So I need to get zeros in the second entry on the first row and 0 in the second entry on the second row. So to do that, I'm going to take row 2 plus row 1 to give me my new row 1. Since row 2 is my leading one, I'm going to keep it the same. So I'll just copy it down. And now to get a 0 in the second entry of row 3, I'm going to take 4 times row 1 and add that to row 3 to get my new row 3. Oh, sorry. I said that wrong, didn't I? -4 times row 2 plus row 3 to get my new row 3. Okay, our next step is to get our third leading one, which is already done. So I'm going to move straight to getting zeros in all entries above that third leading one. So that's my next step. Okay, for row 1, I can easily do this by adding row 3 plus row 1 together to get my new row 1. And for row 2, if I take row 3 and add it to row 2, that also yields me my new row 2. And so notice I have the identity matrix on the left-hand side of this problem. So after the dot dot dots, everything that's left, that 3 by 3 matrix, is my inverse to my original function. So I could say, therefore, my inverse of matrix A is equal to -2 times -3, 1, -3, -3, 1, and -2, 4, 1. And you found the inverse of a 3 by 3 matrix using Gauss-Jordan elimination. I want you to try this one. Okay, set it up by copying down the given matrix. And dot, 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 you'll have the identity matrix on the other side. Okay, so I already have a leading one in my first row, first column entry, so I'm going to get zeros in the row below. Now row 3 already has a 0, so the only thing I have to do is work with row 2 by taking -3 times row 1 and adding it to row 2. Next step is to get my leading one in my second row, second column entry. Now it looks like, since if I did dividing that row 2 by 1/2 or divide by 2, I get some fractions. So what I'm going to do is I'm going to interchange my row 2 and row 1. And now if I simply multiply my row 2 by a -1, I will get a leading one in the second row, second column entry. All right, so I have my leading one for my second column. So now my goal is to get zeros in the column above and below that leading one in my second column. I can do that by taking the opposite of row 2 and adding it to row 1 to get my new row 1. And then I can take -2 times row 2 and add that to row 3 to get my new row 3. And I now have a leading one in my third row, third entry. So all I have left to do is to get a 0 in my third entry on my first row. I can do that simply by multiplying -1 times row 3 and adding it to row 1. So therefore, I found my inverse matrix. So this method works very well when you have a 3 by 3 or greater matrix. But for a 2 by 2, we have a shortcut that we can use that saves us a little bit of time when we don't have to do guessed-sorted elimination. But this only works on 2 by 2 matrices. So if you have a 2 by 2 matrix, I'm going to label the entries A, B, C, and D respectively. To find if A and B is invertible, you're going to do multiply the diagonals down minus the product of the diagonals up. And if that number is not 0, then the 2 by 2 matrix is invertible. If you get 0, the 2 by 2 matrix is singular. And then to find the inverse, if it does have an inverse, the inverse of this matrix A would be 1 divided by the product down minus the product up. And then you would write a new matrix that you'd multiply this. Now the diagonal down, the A, B, A, D, we're going to switch those entries. So D is now in my first row, first column entry. A is in my second row, second column entry. And for the diagonal up, you keep the numbers in the same spot, but you negate them. So C becomes negative C, and B becomes negative B. So you do the opposite of whatever sign that is. Okay, and then you just simplify this down. So that would be our inverse of matrix A. So let's see how this works in a problem. So here is a 2 by 2 matrix. So to find our inverse, I take 1 over the product of the diagonals down, so 2 times 3, minus the product of the diagonals up. Multiply by the diagonals down, I switch my entries. So it's going to be 2 in the first row, first column entry, and 3 in the second row, second column entry. And then the diagonals up, I negate or do the opposite of. So it's going to be 1 and a 2. Now I'm going to simplify this matrix down. So I'm going to start by figuring out what this fraction is. So that gives us 6 minus 2. And 6 minus 2 is 4. So I have 1/4 times 2, 1, 2, 3. And so I just have scalar multiplication. So I'm going to multiply each term by a fourth. That gives us 1/2, 1/4, 1/2, and 3/4. And this is the inverse of matrix A. So that's how you find a 2 by 2 inverse. All right, you try this one. So to find inverse of matrix B, I'm going to start by taking 1 over the product of the diagonals down minus the product of the diagonals up times by the matrix where I switch the terms on the product down. And so that becomes my first entry, first column is 2. My second entry, second column becomes 3. And then the diagonals up, we negate. So negative 6 becomes positive 6 and negative 1 becomes positive 1. Okay. Simplifying the fraction outside first, I end up with 6 minus 6. Well, 6 minus 6 is 0. When you get the 0 in the denominator, because when the product down minus the product up is 0, this function is not invertible or it's singular. So it has no inverse. So you would write B is not invertible, or you would write B is singular, and you are done. Okay, we know that a system of linear equations can have exactly one solution, infinite many solutions, or no solutions. If the coefficient matrix A of a square matrix, and this is a system that has the same number of equations as variables, is invertible, so it does have an inverse, then the system has a unique solution. So only those ones that the matrix does not have an inverse will we have either the infinite many solutions or the no solutions. So anytime that we set this up, if it's invertible, it has a single solution. So that is, if A is an invertible matrix, then the system of linear equation represented by A times X equals B has one unique solution, given by X times the inverse of A times the B. All right, let me translate to what this means in our situation here. So first, we're just going to set this up. So I'm going to practice setting up. So that matrix A stands for our coefficient matrix. And we already talked about what a coefficient matrix is. Matrix B, X is referred to as our variable matrix, and B is our constant matrix. So how would I set up example A here? So we would start by our coefficient matrix. So remember, our coefficient matrix is the coefficients of the variables, not including the equal to sign. So remember, that was the difference between our coefficient matrix and then our augmented matrix that we learned last section. Okay, now I'm going to times this by, we're going to have a column matrix that is just our variable. So our first, in the order in which we're writing, so our x was written first, so it's in the top, then our y, and then our z is our last entry. Okay, and this is going to equal to another column matrix, but this is our coefficients matrix. So that's where we put our answers or our coefficient terms. This is the system of matrix equations. This is the matrix equation for this system. So I want you to try this example. What would be our matrix equation for this system? Okay, we start by making our coefficient matrix, which is 3, negative 4, 5, negative 2, 7, 0, negative 5, 1, negative 1. We're going to times this by our variable matrix. And our variables are x, y, and z. And this is going to equal to our answer matrix. And that's how you set it up. Now, so these two examples, since they were a 3 by 3 coefficient matrix, I would then have to find the inverse of this coefficient matrix by using our Gauss-Jordan elimination technique. But for the examples that we're going to do next, I'm going to use a 2 by 2 systems of equations so we can use that shortcut of finding the inverse that we learned last class. So let's start by making our matrix equation for this problem. That would be our coefficient matrix times our variable matrix equals to our constant matrix. And then by definition, this is going to be equal to our variable matrix is equal to the inverse of our coefficient matrix. So off to the side here, I'm going to figure out what the inverse of my coefficient matrix is. Okay, so since this is a 2 by 2, to find its inverse, I'm going to take 1 over diagonal down, the product of the diagonal down minus the product of the diagonal up. Okay, remember to find our inverse of a 2 by 2 matrix. I take 1 times the product of the diagonal down minus the product of the diagonals up, and then we invert it. And I get negative 1/7 times by 2, negative 3, negative 3, 1. Distributing that negative 1/7, I get negative 2/7, 3/7, 3/7, and negative 1/7. So that is now what I put over here as my inverse of matrix of my coefficient matrix. And I need to multiply this by my constant matrix. And so our answer, our variable matrix, xy, is going to equal to this product. And so I got negative 2/7 times 22 plus 3/7 times 10. And that's my first row, first column. So now I'm going to do second row, first column. 3/7 times 22 plus negative 1/7 times 10. Simplifying down, I get negative 44/7 plus 30/7. And for the second row entry, I get 66/7 minus 70/7, or 10/7, sorry. And that simplifies down to negative 2 over 8. And so that tells me by our equal matrices, x must be negative 2 and y must be 8. So the solution to this system is the answer negative 2, 8. All right, you try the next example. First, I want you to set it up. All right, our coefficient matrix is 2, negative 3, 1, negative 1. Times by our variable matrix, in this case xy, equals our constant matrix of negative 112. Step 2, find your inverse of your coefficient matrix. Please do that. All right, so that's 1 over times the diagonal down minus the product of the diagonal up. Switching the diagonal down, negating the diagonal up. And that becomes 1 over 1. And so our inverse matrix is simply negative 1, 3, negative 1, 2. Now we're going to set this up as my variable matrix is equal to my inverse of my coefficient matrix times by my constant matrix. And now we just do our product here. So negative 1 times negative 1 gives me 1, plus 3 times 12 is 36. And then we have negative 1 times 1 is 1, plus 2 times 12 is 24. And so xy is equal to 37, 25. And our conclusion, therefore, is that x is 37 and y is 25. So now I want you to try this one by solving this system, this 2 by 2 system matrix using our matrix equation that we just learned. So step 1, set up your matrix equation. Recall that our matrix equation is our coefficient matrix, which in this case is 2, 3, 1, 2, times by a variable matrix of xy, equals our answer matrix of 11, 6. And then therefore our variable matrix xy is equal to the inverse of our coefficient matrix. So let's find the inverse of our coefficient matrix. So that's 1 over the product of the diagonals down minus the product of the diagonals up. And then to set that up, we're going to switch our diagonals down and negate our diagonals up. Okay, so 2 times 2 is 4, and 3 times 1 is 3. So I got 1 divided by 4 minus 3 times by our matrix here. And then 4 minus 3 is 1, so that's just 1. And so distributing a 1 to this matrix just gives us the matrix 2, negative 3, negative 1, 2 as our inverse matrix. And we're going to times this by our constant matrix of 11, 6. So our variable matrix is equal to, okay, we're going to do 2 times 11, which is 22, plus negative 3 times 6, which is negative 18. And our second column, our second row entry will be a negative 11 plus 12. Simplifying that down, I end up that we have 4, 1. So therefore, x is 4 and y is 1.